Okay, so here's the topic for today. And you know, it is, like it was said before, it is St. Patrick's Day. So happy St. Patrick's Day. I know there's probably a few of you in the room that may have already started to drink. So I'll do my best to not give you an additional reason to drink. So the slide we thought should look more like this, since it is St. Patrick's Day. The funny thing is I actually forgot to wear green, but at least Einstein has green on. All right, so today I'm going to talk about really like my journey in just different topics in research and really technology development that I've interacted with and intersect. And as part of that, the kind of core thing that goes across that is this desire to invent, this desire to do something useful. I mean, that's why I got into the sciences, and that's kind of what took me from an academic setting to startups. And doing some of the things that I've worked on and contributed to. But one thing that'll come up a lot is this idea of a particle. And so I want to start with a video, and I'll play it here in a second, but what's on this, this is a microscopy video. So this is on a microscope. In fact, it's just right down the walkway in the chemistry building and Professor Raoul Coltman's lab. This is where this was taken. And what you'll see is there's some bacteria and magnetic particles. So that's the magnetic particle. And you see the magnetic particle is moving around. Well, what I'm doing is I'm taking one of these big rare earth magnets and just bringing it near to the microscope and just essentially tugging on the magnetic particle. And then what happens is you can see let's see if I can get this to play again. What happens is the bacteria that are attached to that magnetic particle move as well. So it's like, okay, those are bound, or they've bound together through some mechanism. And one question I get a lot when I show this video is like, well, how did they bind? So that magnetic particle actually has antibodies on the surface. Those antibodies are specific to a surface molecule on the cell, in this case an E. coli cell. So this is actually literally the E. coli that makes your stomach hurt. So you have to be careful when you're working with these. But it's like a biological lock and key. And so you can start doing these really interesting systems, and as a scientist and physicist, I look at this and I go, oh, now I can start having fun. So you can pull on it, you can try to measure the bacterial force, you could measure all kinds of things. And this is the kind of stuff I was working on in graduate school. And in the same lab, during my PhD in Coltman's lab, we were working with these particles, and we started doing some interesting things with them. And I just thought before, so you've seen what they look like on the microscopic scale, but I thought it'd be nice also to take a look at what these look like on the macroscopic scale. So we'll do a few demos, and then I'll get into a little bit of some interesting applications of magnetic particles. So to start with what I like to call the wonder of magnetic particles, we have a demo over here. So instead of having a regular salt and pepper shaker, physicists like to have a shaker full of iron filings. It just happens to be laying around. And what's shown here is a solenoid. So it's just a wrapping of wire. And so what I'll do here, let me turn this off. I'm just going to shake some iron filings around that, just kind of randomly oriented. And if I get this right, something interesting will happen when we turn on the current that's running through these wires. When the current goes through the wires, that creates a magnetic field. And so I would direct your attention to kind of the center line there inside the solenoid. And so let's just watch what happens here. Nothing, like typical science right now. So they should line up. Let's give it a second. Let me, if I tap this. Oh, I didn't close the switch. See, that's why the demo lab is here. So it's on now, and now I'm going to close the switch. See, the thing you learn is every first experiment usually fails, so you just keep going. All right, so I'm gonna flip this switch. So let's watch what happens in the center. Okay, do you see that? They all line up. And you can see that it's essentially uniform inside of there. And if I tap this a little bit, we might be able to see the top and bottom lines start to form. And if you can tell, there's sort of this, they're going up and then kind of curving out. And so what we're seeing is the magnetic field lines. Okay, so what's happening is those little magnetic particles are trying to line up with the field. They're experiencing some force. And in physics, we love forces. We draw these force diagrams all the time. And so to visualize that a little bit further, we have a three-dimensional version of this. So has anyone played with ferrofluid? Any ferrofluid people? Okay. So that's what we have. We have some ferrofluid, which is just essentially those magnetic or the iron filings in an oil. And so let's see here if I can. So right now there's no shape to it. Let's see. And if I bring it, underneath here is a rare earth magnet, so a very powerful magnet. And if I got to turn on the light. Thank you. Another switch. You can see why all my experiments just never work. It all makes sense now. I get it. I understand why graduate school takes so long. All right. All right. So I'm going to bring the oil with magnetic particles, which you see is just flat. And if I put it on top of the magnet, it'll form a shape. And do you see all the little spikes? So each spike is essentially trying to form along a field line. And all those magnetic particles are trying to jam themselves close as possible to the magnet. And in physics, we call this a gradient force. So what that means is when there's like more of those field lines like we saw over there, or what's shown here, the higher the density of field lines, the more force there is for the magnetic particles to go toward. So what that means is if I start to pull this away, we should start to see more, or actually less of those spikes. So as I move it away, the number goes down because the density of those field lines are going down, which means the force is lower. And so this is a really interesting thing, and we could keep going, which you just see a few now. You see that? Okay. So if we go back again, so we're actually getting something of a 3D image of what the field lines are doing there. And so what that allows you to do, the reason I wanted to show this to you, is again, these are like the same type of particles you saw in that video. So you can kind of get them on the individual level, and you can do all these fun things. But on the larger scale, they look like this. What's interesting about that is you can then do something called magnetic separation. So now I will remember the switch. So the third time's a charm for experiments. Okay, so what we have here is now a fluid, not oil, but it has these magnetic particles in it. So I'm just going to shake it up. And what we do in life sciences and how people actually use magnetic particles, and I mean, you could call it magnetic fluid, but it's a little bit more dispersed, is if I have a tube like this and say I have a sample of blood. And that sample of blood is a mixture of all kinds of things. There's proteins in there, there's DNA, there's cells. And what if I want to just go get one thing so that I can study it? What if I just want to study the DNA? What if I just want to study the proteins? Or what if I want to grab the DNA so I can diagnose a disease? So a tool that's been developed is to actually use magnetic particles to bind, say, to that DNA or to those cells, and then you can magnetically pull them out. And that's all based on this idea of gradient force and how magnetic forces work. So you ready to see it? Okay. So I've mixed that up. So I have a very powerful magnet, which I love these signs. Anytime you're doing something that says danger, as a scientist, you get a little bit excited. All right, so we have a magnet. That's why there's the danger sign. Okay, so keep your eye on the left, the smaller tube there, as I bring the magnet close. So imagine that those are attached to some sort of, see it goes clear, which means all the magnetic particles and whatever's attached to them have now come to the side. And if I was in a lab, I could hold the magnet in place, I could pull the fluid out, and then put fresh fluid in that's now clean, shake it up, and now I have my isolated proteins, DNA, cells. So let's actually, do you want to see that again? I always like to see cool things more than once. All right, so again, I'll bring it over here, and you can see it goes clear. And another interesting thing, though, is, so that's just translating, right? That's just moving toward the magnet. A cool thing you can do is actually, what happens if I rotate the magnet? Let's see if I can get my north-south right. So do you see what's happening there? As I rotate, those particles are wanting to rotate with the magnet. And so, like I said, as a scientist, you get a certain setup, and you just want to start trying different experiments. Ideally, that leads to something useful, or you're doing it for useful reasons. But the point is, if I rotate this, the magnetic particles rotate. If I bring the magnet close, the particles come out, and you can do all kinds of fun things with that. One of those fun things is what I have next here. So this is I got to switch over. Thank you. Luckily, I don't have to push the button for that one. Okay, so what's shown here is a single magnetic particle. So again, if we zoom in on one of the particles in that fluid, and then look at how it behaves. So when I was working on my PhD, one of the things I was doing was looking at individual particles and rotating them. And what would happen, as you'd expect, if I rotate around the magnetic field, like that big rare earth magnet, once per second, what speed would you guess that the particle would rotate at? Once per second. And that's actually what we'd seen on the microscope. That's everything we understood. And that's what I was doing in the lab. And what's plotted here, there's a plot that will show up. The y-axis there is the rotational speed of the particle. The x-axis is the rotational speed of the external magnetic field. Okay, so what happened was I was just starting out. I was an early grad student, and I was very curious to know what would happen if I just cranked up the speed. I wanted to see how fast could we go. And keep in mind at this time, the setup was, it wasn't an electromagnet, it was actually a magnet attached to a motor. So I started rotating at a low speed, and I started rotating actually so fast. And here you can see they're rotating at the same speed. The leading arrow is the orientation of the magnetic field. The other one is the moment of the magnetic particle. So we started cranking this up, and the thing started shaking, and I took refuge behind the microscope, a very expensive microscope. But what happened is something funny happened. If you watch at a high speed, it starts to go asynchronous. It actually can't keep up anymore. But what's interesting is it keeps rotating. So if I keep plotting the speed, the faster I rotate with my external magnetic field, the slower the particle rotates. And anytime you see this kind of effect, what you see is the sort of left side of that plot is a linear response. On the right side is a nonlinear response, meaning it doesn't go up anymore as I increase the field. There's not this like one-to-one relationship. And what's really cool is that you can keep going up really fast, and then the particle just starts shaking. But if you wait long enough, it'll actually eventually go around. So we'd never seen this before. We didn't know of anyone else who'd seen this before, and it felt like something of a discovery, a very maybe small micro-scale discovery. But it was interesting, and we thought, wow, there's this really sharp point on that curve. We wonder what that, like where that point, like what affects where that point is. So like if we changed something about the particle or we changed something about the environment, how would it change where that happens? And then using that, could we use it as some sort of sensor? And also as a scientist, and especially as a physicist, the old joke is the only thing a physicist is good at is measuring frequency. If anyone, okay. Maybe there's a few people who can relate with that. So maybe I don't need to say anything here. I like to say it's easy to measure frequency, and it's even easier, actually, to measure frequency change. So it's cool when you have a sensor that's based on a rotation rate, it's a frequency. So then if something about it changes, you can measure it very easily. So we saw this, and we started exploring it. And so, sometimes when these kind of things happen, you start asking yourself, well, is there any precedence for this? Is there any other systems, maybe, that follow this kind of behavior? And you start exploring. And that's one of the fun things to me about science is I feel like a lot of times science is portrayed as being this very sort of predictable thing where, it's just very, like, repetitive, and you just need to understand the equations. I've actually found that the exciting part about science, other than, of course, understanding the world around us, is that it can be very creative. It can be very fun and rewarding. And so these are the fun times when you see these kind of observations and discoveries, because you can start being creative and thinking about, well, what kind of systems are there? How are we going to model this? How are we going to write the equations? So it turns out that there's a couple things that behave in similar ways as what you saw in the previous video. One is actually motors. So after doing this for a while, I realized, wait a second, I think we're just building motors. And if you're familiar with motors, often, especially electric motors, you have something called a stator and a rotor. And so I'll show you what that means. So in this motor here, this is called a brush motor, a DC brush motor. What's happening is you have your stator, which is generating an electric field, and then you have your rotor that's essentially rotating in response to that field. And what's happening in this one, those brushes allows the magnetic field to flip, causing the electromagnets in the center to actually rotate. Another kind of motor is called a DC brushless motor. Has anyone heard of a DC brushless motor? So those are used, if you see the, nowadays you see I don't know what they're called, drones, but the quadricopters. So those commonly, actually what's allowed those to happen and to get the lift power they need, they use DC brushless motors, because how those are set up is the stator is actually a rare earth magnet, often like this, or something strong. And then you might have electromagnets on the outside. Usually there's more than just a set of two, there's a set of more. And so that's another kind of motor, and it turns out that actually works in a similar way. Another thing is called an induction motor. So an induction motor is a motor where the rotor is always going slower than the rotating magnetic field. So again, you start exploring some more, and that's neat. So it's not quite just a motor, but it's kind of like a motor. Another fun example is fireflies. So one of my favorite things of living here in Michigan is seeing the fireflies in the summer. I mean, it's like they're pretty mesmerizing, and bioluminescence itself is just fascinating. But it turns out there's a kind of firefly. This firefly in this video is actually from Thailand. But let me turn this down for a second. And so these are fireflies that synchronize with each other. There's actually specific species where they'll start to synchronize. And so what this artist did is he actually, and there's scientists who've done this as well, they built an LED, okay, that could blink at a set frequency. And what happens is when a firefly, so there's the LED, when a firefly sees that, it wants to blink in unison. So that's actually the LED in the firefly there. What happens is if I increase it, they're asynchronous. They can't keep up, just like you saw with the magnetic particle. I personally find it compelling when you see this kind of behavior in different systems. And here you can see now there's fireflies blinking in unison. And if you keep scaling out, you can actually see them doing this in trees. They're not quite synchronized yet. But I'm actually just going to let this video play for a second. Some of this footage was actually taken from Michigan State. They did a collaboration. And then the rest, again, was in Thailand. So here's a tree, a little bit asynchronous. And I'm just going to let it play probably for another 30 seconds so you can watch the synchronicity of the fireflies. So there it is across many trees. See that? I don't know. I find that amazing. I still have never seen this. I want to. It's a good excuse to go to Thailand, Asia. So that's a behavior that exists. And again, that's very compelling because it's, again, a system that behaves in a similar way. Now, just really quick before getting to the equations behind this, I just want to thank Robin Meyer. So he's actually the artist behind this, one of the artists. There's actually a documentary going on right now. He allowed us to show this video in the presentation today. But it's actually, if you're going to be in New York, at Arsenal Contemporary, they're showing the documentary right now until April 22nd. Also, a little bit closer to home, it turns out there's another species of firefly. It's perhaps maybe not as compelling as the one you saw before, but they still synchronize. And then that's in the Great Smoky Mountain National Park. And you can go down there and see that. It turns out there's actually other areas where they can occur, maybe a little bit less known and a little bit maybe not as popular. So I'm still waiting for somebody to find some synchronous fireflies in Michigan. So if there's any eager explorers out there, do us a favor and find some synchronous fireflies closer to home. But you know, who knows, right? So if you like walking in the woods at night looking at fireflies, you might find a grove with the species that does this. I mean, that's the beautiful thing about science is there's still things to discover. There's still the opportunity to explore. So this behavior of the fireflies, of rotating magnetic particles even, it's a slightly different case, of Josephson junctions, of a certain kind of pendulum. Those are all described by something called the non-uniform oscillator equation. And if you're interested in the details, there's a really great book by Stephen Strogatz called Nonlinear Dynamics and Chaos. And it talks about some of these things and formulates some of the basic equations behind it. And then we basically took that and started thinking about that and applied it to our case of a rotating magnetic particle. And what we found is this, that again, in that sort of linear regime or the synchronous regime, if the particle is rotating at 1 hertz, it's because the field's rotating at 1 hertz, that they're the same. So if I change something about the particle, or if I increase the viscosity of the fluid, nothing happens. The particle just rotates at the same speed. But above, so after that sort of sharp point in that curve I showed before in that sort of asynchronous area, the rotational rate of the particle is proportional. So that's, if you're not familiar with that sign there in the middle, this one here, it's the rotational rate of the particle is proportional to the inverse of what we call the effective volume. So the effective volume is essentially the volume of the particle plus its shape, right? So if I have like a rod rotating, it has a different shape as a sphere, and those may have different rotational rates even though they're the same volume. So seeing this, you start going, oh, okay, well, we could do something where we change the volume, and we could then, sense volume changes. And another way to think about this, is, okay, well, an easier way, maybe just think the period of rotation just goes proportional to the volume of the particle. And so that's really what, I decided not to show the full equations here. Again, if you're interested in that, you can look this up, you can get Strogatz's book. But this is what really I want you to remember, is that the period of rotation in the system depends on the effective volume. So to see that, to visualize that before I show you an application of this on the microscope, we have a Hoberman sphere. So keep in mind, this is dominated by momentum. So this is, at this size scale, inertia matters. But what that equation said is if we change the volume, right, that the rotational speed changes. So we'll see if I can reach, because I'm going to start this one a little bit different than how it's normally started. So I'm going to start it small, like our small particle. If you could go down a little bit more. Yeah, a little more. Okay, good, thank you. See, science in action. Okay, so we're just going to spin this. I'm going to try to give it a really good, I'm going to try to give it a really good spin here. So as I relax that, see how much it slows down? So by a huge amount. I don't know if anyone was counting, but that's got to be like a factor of 10 or so. And if we pull it back, let's see if I do it careful enough, it'll start speeding up again. Okay. So it's the same type of thing. If I change the volume of the magnetic particle, making it bigger, it rotates slower. And just for fun, we'll start big and go small. I don't know how many have seen this demo. It's a pretty fun one. My son, when he saw this, said, "Are we taking that home?" And I said, "No, it's the demo labs." So if it disappears, you know where it went. Just a forewarning. Okay, thank you. Okay, so what if, again, we do this now on the microscopic scale. We take one of our magnetic particles, we set it to rotating, and we let bacteria bind, or we let bacteria that are bound grow. What happens? And so using these dynamics and using these principles, now again, in the magnetic system, it's actually drag that dominates, not inertia. So this is rotational period. So if a bacteria comes along and sticks, it slows down. And you can do that with a single bacterium. And if you leave it there, you could actually let it grow. And then you can get single cell growth curves. And then what's cool about that is if I add antibiotics, I can stop the growth, and then the rotation rate is steady again. So that was our idea. We started with this basic behavior of magnetic particles rotating in a magnetic field, again, using physics, and from that, getting an understanding of how this could behave, and then doing something with it, applying it, again, in the spirit of applied physics, to a biological or life science setting. So could we actually do this? So, well, here's a magnetic particle. This is 2.7 microns in diameter, and there's a single E. coli attached. And what we're going to do, I'm going to show this in real time, what's going to be happening, what you don't see is that there's a magnetic field rotating at 100 times a second. Okay, 100 times a second. So let's see how fast this rotates. Okay, so you see that it's on there. I like to think this is the best life a bacteria ever had. It's like being at the carnival or something. But it rotates about once every 2 seconds. And what happens if we just let it grow then? Okay, so this is the same bacteria a few minutes later. So you can see the bacteria is longer. And the rotation rate now, or speed, period, is 2.7 seconds. So 30% longer. And you could just, what's so cool about this is I can just set it and keep watching it. So what happens if we just keep letting this happen? The bacteria now has grown into 3, and they're all still attached. But at some point, they're going to divide. And so watch this. Watch what happens to the rotational period and speed when it divides off. It goes way faster. So all of a sudden, you have a system using physics that's incredibly sensitive to any minute change of a cell that's attached to it. You could do this with viscosity changes. You could do this with all kinds of things. And we did all those things, and they were fun and exciting. And to actually see what this looks like, I won't spend very long talking about this, but I'll just draw your attention to the lower plot here. This is the rotational period over time. And so you can see that if you normalize initially to 1, that you can get these huge changes over a single division of a single bacteria. Okay, so that's exciting. And as a scientist, again, as I remind you at the beginning, I said, yeah, I got into science because I wanted to do something useful. That's actually how I've lived my career. And when I say useful, I don't mean like other things aren't useful. I mean that everyday people can put their hands on. And so that's always how I think about these things, is how can we get it out? And to me, it's really a way of getting fundamental research to be out and disseminated even further than, say, just publishing a paper. So we published a paper on this, but we wanted to keep going. And it's like, okay, well, what's useful about this? Well, what's useful is if I can very sensitively measure the growth of a bacteria, I can very sensitively measure its response to an antibiotic. So right now, if you have an infection, you'll go to the hospital and they'll take a blood draw. And at the fastest, if like the stars align, it takes them 2 days to determine what's the best antibiotic to stop your infection. Because they first have to isolate the bacteria, then they got to grow it, then they got to see how it responds to the antibiotic, and then they know what's the best antibiotic for you. And so the first company I worked on was called Life Magnetics. It was based on this concept and this need to make that test faster. So the idea is you get to the best antibiotic as soon as possible. So to see what it looks like with antibiotics, the one on the left is below a critical concentration of an ampicillin, and to the right it's above it. So the one has been dead for a while, the one on the left is growing, and you can see the one on the right is rotating faster. And you can start building these systems to think about, okay, let's actually make now something we could do as a test. So a lot of what you saw was on the microscope. But a fun thing that happens is when you ask the question, how do we get this out there, you have to then learn how to build it. And then a way that's reproducible. It doesn't just work once in your lab. It works every single time. And so this is where engineering comes in. So what's shown here is, so this is an array of inductors. So just like if you remember here, you could actually call these inductors, and there's off-the-shelf electrical components that you can just put on a circuit board like there, and if I put them in that kind of arrangement, 2 at each pole, I can create a rotating magnetic field. So that's what we did, and in between there, we'd have our samples. So that's one thing we had to do is how do we actually rotate the field? So the other thing we had to do is figure out a way to measure the rotation. Now keep in mind, these things are 2.7 microns. So what's the engineering question that takes you from being able to measure something on a microscope that's 2.7 microns to something where maybe you could just use an LED and a photodetector? And the answer is what's shown here. We actually wound up using self-assembled groups of magnetic particles, anywhere from 50 to 100. And those were sensitive to just a handful of bacteria. And we'd bring those together and we'd rotate those as a unit, and then when you shine light through those, it essentially blinks the light. So again, being a physicist, you get excited because you can measure frequency. And so we did that. And we crammed that all into this system here, developed a disposable cartridge, a unit to measure all this, plug it in the computer, perform measurements. So putting this all together, and now keep in mind, don't forget about the magnetic separation. So now I have a way I can use the magnetic particles to go in blood, I can grab the bacteria, I can put it in the system, and I can measure the presence and growth of those cells very easily. So again, here's a magnetic particle. This would be like a blood sample. So there's all these cells floating around. The bacteria are attaching to the magnetic particles, the ones you want to capture. Once you have that, like the demo that was over here before, you can pull those all to the side. Okay, so you can do the actual magnetic separation. So these are all coming over. We'll zoom out here in a second. So all those are against, you'd use a container like the one was shown there. And that's happening because you have, again, a magnet outside, all the particles to the side. And when you have that, you can remove all the fluid with all the cells and junk you don't want, and then put something clean into that. So now you have your isolated cells that are on magnetic particles, and then you can move on to this asynchronous system, loading that sample into the card, the disposable cartridge, and then placing it into the unit. And I'm just see if I can jump ahead here. So inside, what's happening is, again, it's those spinning particles, and we shine light through those, and that's what's shown here. So each well, we had just an LED and a photodetector. So we were able to go from the microscope to just a standalone system using these basic physics and engineering principles. So here's what the data looks like. If you look at one well, just put bacteria in there, you get growth. And if you have a well without bacteria, it's just flat. Okay. And then at Life Magnetics, we continued on and built more systems. And the exciting thing is we were able to measure growth of these bacteria. Instead of spending hours, we could do that in minutes. So it was really rewarding. It was my first experience working in a startup team. And it was really exciting because you're entirely focused on accomplishing your objective of solving this problem. So that was great. There is a but. And as much as I like magnetic particles, there's some issues with them. Magnetic particles, as cool as they are, and I mean, you saw the ferrofluid, right? I mean, as fun as that is to work in your lab, they can actually lead to some challenges and problems. And so I'll show that in a minute. So I have a demo here. So what's wrong with magnetics? So let me show this first. So how that worked, right? You had your magnet next to the vial, and all the magnetic particles came over. And this is our happy magnetic particle. And this is all the different forces that are going on there. And the magnetic force is when it's close to the magnet, it's the most important one. And the magnetic force scales with a magnetic field squared. And so then as that gets smaller, as I move away, it's not like a linear type drop-off of magnetic field. It's actually much more dramatic. So it looks more like this. So you got your sad magnetic particle there because it's not anywhere near the gradient. So I like to think of no particle left behind. So to show that, just turn this light back on. So you remember this guy, which we saw. So I have a much bigger container of magnetic particles. Okay, so let me just shake that up. So let's see what happens, right? This is what science is all about. You do the measurement. So let's just see. Okay, so I have the magnet. All right, bring it close. Okay, it's not exactly behaving as it was before. It's starting to clear up a little bit, and let's see if we can see the magnetic particles in there. So you see the clump that's starting to form? I can bring it up front. So that's not beautiful. All right, so, but you see that the fluid is still can you see how cloudy it is? So it's not working the same way. So anytime you see those things, you ask yourself why, and the why, which we already talked about, is the gradient force. So think about out here, just like you saw with the ferrofluid, the lines aren't as dense, so the force isn't as strong to pull those particles there. And if I leave this, in some cases you leave this here forever and those particles never come out. They'll actually sediment before they go to the magnet. So that's a problem. What that means is there's a limitation of how much fluid you can actually process. And so people have tried to overcome this because, and I'll say in a second why it's a problem. There's been actually companies that have tried to solve this, and scientists as well. So one solution, you could say, well, use a bigger magnet. Right? Give me a huge magnet, and we'll put it around here, and you're going to need a bigger one of these, much bigger one of those too. You need a bigger one of those. You're going to have, and in fact, there's a company that does it. It's a cool company, but you got to have this giant magnet for every one of these that you want to process. Okay, that's one way you solve it. You put a big magnet around it. Another thing we could do, you might say, well, take that rare earth magnet. I told Monica I wouldn't do this, but you could drop it in the fluid. That would be a cool demo. Next time. So I could drop this in the fluid, and maybe I could shake it around, and the magnet would float around in there and grab all the particles. And there's actually a product even that does that, and a company and scientists. Another way you could solve it is you might say, okay, well, wait a second. What if you made something to pour the fluid all over the magnet? Sort of doing something similar to the second one, but just pouring the fluid over. And so people have done this because this matters. And I'll say in a minute why, but there's a problem with all these in that they're not easy to work with. You sort of have to change what you're doing in the lab, working with cells, to be able to do these things. And so we decided we wanted a better way. It's got to be a better way. Edison would say there's a better way, go find it. And so that's really at the heart of Acadium, and what we're all about is how do we find a better way. Maybe it's using magnetics. I mean, we thought about that initially. Maybe it's doing something else. But we wanted to find a better way. We wanted to be able to process any volume. We wanted it in something easy, something simple, maybe even something that's gentle to cells, that doesn't basically make the cells angry. But before talking about Acadium and what we do there, let me just motivate why you want a larger volume. So this is just one example. So has anyone been following the story of CAR T therapy? You guys heard about this? Sometimes it's called CAR T cell therapy. There's actually an FDA-approved, there's actually an FDA-approved process one now doing this. But it's the idea of using your own immune system to treat disease. So your immune system is miraculous, right? I mean, it can do, there's so many nuances to it. I mean, it can do amazing things. And so the process of CAR T cell therapy is you basically pull white blood cells out of the body. You then isolate T cells, so you got to get a subpopulation. And then you can actually engineer them or train them to attack only the cancer cells or to attack the cancer that you have. And there's a whole beautiful science behind that too, which I'm not going to go into. But you engineer the T cells. Then once you have your engineered and isolated T cells, you can grow them and essentially scale up how many cells there are to the point where you can put them in a unit and infuse them back into your body. And also with some chemotherapy. Got to throw that in at the end. And what that does is it destroys the cancer in your body. And it's been working incredibly well. It's one of the hottest things right now in therapy. So it's not a drug. It's basically training your own immune system to treat your own disease. And to do that, though, you can't use this much material. You have to use this much material. So now if you want to do this kind of thing, which right now takes 17 days and $500,000 for the FDA-approved process, there's a lot that goes into it. So wouldn't it be nice if we could start working on simplifying that? And one step is the separation and isolation of cells. So that's just one example. There's others. Imagine that you want to test, a truck of ground beef or a truck of spinach for bacteria that can kill you, like the E. coli I showed in the beginning video. You actually would rather have this much fluid, not this much fluid. There's other examples. There's diagnostics where you're looking for DNA. I mean, the list goes on. And that's just one area where we need to solve the limitations of magnetics. And I'd like to spend a few minutes kind of thinking through that and how we might solve that and kind of how we wound up solving it at Acadium. So in a blood vial, there's this huge mixture of cells. I mean, cells are classified in different ways, but I mean, think about hundreds. There's not just like 10 different cell types. There's types and subtypes and all kinds of different things. And here's just a few. And by the way, I love this quote here that the natural forces within are the true healers of disease, which is like, I feel like what CAR T-cell therapy is all about. But one thing my business partner, John Younger, likes to compare to is this bowl of 1 billion M&Ms. Okay, so the problem is, in that vial you saw on the previous slide, you have all these different cells, and there's literally billions. So the challenge is, okay, go get the 1 million cells that I want out of 1 billion. So that's like having a bowl of 1 billion M's and me just saying, get the blue ones. And to look at the actual numbers, in just 1 milliliter of blood, and if you're not familiar with what 1 milliliter looks like, you could say 1 cc, but this is probably 4 milliliters of fluid. In just 1 milliliter of blood, there's billions of red blood cells, almost 1 billion platelets, and maybe 4 to 11 million white blood cells. Okay, so keep in mind for something like CAR T therapy, we need not white blood cells, we need T cells. So it's even a subpopulation of those white blood cells. So it's only like, of that, it's only like 0.1%. So it's kind of a fun engineering and physics question of how do you do that? So, I like to think of it as like this, this pile of 1 billion cells. Go get the valuable ones. We just care about these. So I grew up in California. One of my favorite times in history is the gold rush. So I grew up gold panning. So I like to think of it like this. So in 1 million grams of dirt, you want to go get something valuable, which actually a good mind from what I understand, a ton of material, if you get 10 grams of gold, it's pretty good. So it's actually not too dissimilar of a problem. You have this big hunk of material, and you want to go into it and get something valuable. So what do? How do you think about this? How do you solve it? So let's think about that for a second. So okay, we want to go get those cells. How do we do that? The first thing is you got to decide what you want. So in the pile of dirt scenario, you want gold, but there could be silver in that. There could be platinum. There could be other things. Same thing with cells. Which cells do you want? Do you want the stem cells? Do you want the cancer cells? Do you want the T cells? Do you want the B cells? You got to decide what cell you want and have figure out a way of classifying that. And then, this is where physics comes in, you could figure out a way to get those out. And so that's really kind of the architecture of the way I like to think about it. So for the first step, deciding what cell you want, there's just one thing that's interesting to know before we jump into this called immunophenotyping. And so how you actually classify the different cells is by those we call them surface markers. CD stands for cluster differentiation. And the idea is, like white blood cells all have this thing called CD45. And I don't think there's like a reason that CD45 is white blood cells. That's just the nomenclature, and they sort of started at CD1, CD2, CD3 as they looked at the different molecules on the surface of white blood cells. And what's interesting is, like, if you look there on the left, the stem cells at 34, then everything after that on the white blood cells have CD45. But then what would differentiate, say, a T cell from a B cell is one has CD3 and the other one has like CD4. And what's cool, if you remember back to the antibodies, I might be able to use antibodies to attach those and do different things. But that's, you got to pick something that you want first. Then the second thing is going and grabbing those. Or I like to think going and grabbing those. There's other ways to do it. But I like to think of it more broadly and like, okay, what's the physical properties of the cells that allows you to go and differentiate one of those populations over the other? Okay, So one is, like I showed on the previous slide, you could actually grab onto the surface molecule and pull it out or do something. Another is size and shape. So, the cells aren't all equal. They're different sizes, and so maybe you could do something with its size and shape. So another here, I don't know if anyone's ever cultured cells in the lab, but it turns out certain cells stick to plastic, other ones don't. So that's our monocyte who's stuck. These poor cells. All right, and the T cells aren't. So there's other things you could do to further differentiate those, and people do these. These are real processes, and I'll show that in a second. Another fun one, this is going back like the gold mining, is density. So this is actually a plot of cell number over density. And it turns out different cell populations actually have slightly different densities. So, we could maybe use something to focus in on that. So if you look at like A versus D, I could separate my monocytes from red blood cells. There's a big difference. And so that's actually a method that's out there. Has anyone seen like where they centrifuge blood? Have you guys seen that? Okay. That's the idea. Because when you centrifuge something, you get the different separations. So right now, that's what we actually have here, a little demo of that. There's two different fluids in here, and when I shake them up, they're going to become the same density. But the idea is you want the fluid to be some density that separates two populations. So that's actually, there's this thing called phycol. It's like you basically can put it into a container, like the little one there, put on a centrifuge, and it can separate your cells. So let's see if we can do this. So if we wait a second, what you see is now the fluid is all the uniform density, and it's a magical density that's between the density of these two bits of plastic, and you could say between monocytes and red blood cells. It's the same idea. So then I could come in and just pull those off the top. And that is a real procedure that's done now. It's an older procedure, so people are looking for new ways, again, going back to the whole motivation here of doing larger volumes. So one of the things that's really popular right now is trying to do cell separation and microfluidics. And so here's a few examples. The top, so I'm not going to go into details of all these. I will point out the one on the top right is some work that's done here at Michigan. And they basically use a spiral channel. And they pass fluid through that with the cells. And the idea is the cells will just naturally separate based on size into different streams, really. So it's a pretty cool process and something that's fun to go look up. The one on the bottom right is actually a company as well, and they use density, and instead of using like a fluid to separate different cell populations, they use a little flow. But again, it's a way of trying to separate cells. So a fun little demo in the spirit of Saturday morning physics and doing lots of demos. What you see here is the same fluid. We have a ball that's more dense than the fluid here and one that's lighter. And so this is actually, it's not quite this angle, but this is essentially how a centrifuge works. You spin it, and the heavier stuff goes down, and the lighter stuff goes up. So let's see if we can spin this and see what happens. All right, I don't know if you can see, but do you see the balls now are in different spots? So, and as if we let it go, that one goes back up, and this one falls. So a fun experiment to do in your car is, have you ever driven in your car with a helium balloon? So, and you hit the brakes. If it's not touching the ceiling, which way does it go? It goes backwards. So it's kind of a fun, and also same thing if you turn, you go outward and the balloon goes inward. So it's the same thing. That's actually a fun, and you can use some of those principles, and in fact we have with bubbles, which I might mention in a second here. But we saw this, all these different ways of trying to sort cells. And again, there's equipment required and different things. We thought, can we just simplify this? Can we just make this as simple as possible? Because a lot of times when people perform separations of cells or DNA or protein, they're just doing it to go do something else, like to diagnose a disease or to treat a disease or to study disease. They don't want to spend hours at a centrifuge or hours, on big pieces of equipment. They just want something easy, fast, and simple that you can scale across different volumes. So thinking about this and just being frustrated with the limitations of magnetics, we took to the whiteboard. And we thought, okay, well, let's think about this. So if you remember back to the Einstein, the fishing with the cells, this idea of we need a way to get the cells out, we just said, okay, what are all the different ways we could do it? Yeah, we could stick the plastic, we could try different forces. And we said, well, maybe let's just write all the forces out on a whiteboard. And we didn't last very long because being a physicist, there's only one force. But being an applied physicist, There's more than one force. So you just write it down on the whiteboard. Okay, so you got strong force, weak force. Those probably aren't going to be very useful. You got the electric force, magnetic, which we saw, fluidic forces, which is like the microfluidics. You can think of gravity, and it's like the centrifuge case where you're getting those different populations out. And then we wrote one on the board that kind of jumped out at us. It's buoyancy. We thought that's interesting. We've never seen a method that uses like buoyant particles, let's say, to lift cells. And it was also interesting to us because it's like, wow, gravity is more or less uniform over the size scale of, say, the small vial versus the large one, or something even bigger. So I thought that's interesting. How would we do that? And we said, okay, well, we need to use bubbles. And we kind of laughed, actually, because we'd never seen anyone use bubbles for cell separation or anything like it. And I was like, well, we wouldn't just need bubbles, we'd need microbubbles. And that just kind of stuck with us. And in fact, we laughed at it. We told some people, they laughed. But we thought there's not a physical reason why you couldn't put an antibody on some sort of solid bubble, let's say, grab onto a cell and float it. And so we did that. We did the experiments. We did the tests. And we actually got a system where it was incredibly simple. You didn't need a magnet. You didn't need all this stuff. And what that looks like, so you remember the container of magnetics here. So we have the same container, but now with bubbles. You want to try it? So let's see what happens. And I do have to turn on the light. I'll eventually learn. For next time I'll turn on the lights. So this is just, again, the fluid with microbubbles. So we'll set this here. That's going to take a minute, but I have a smaller one here that will also shake up. See if we can see those all in the video. But the idea is those bubbles are all contained within the vial or the container. So you don't need the magnet, you don't need gear, you don't need anything external. Everything just happens in the container. So if you notice, you can see it up here for those of you who are closer. The bottom is already starting to clear out. The top, you're starting to get a layer of bubbles. So we'll let this go for a second. The left one, you notice, actually, this one right here is already clear. So again, I can do a small volume separation. See if I can move this. Oh, there, do you see that? Maybe do you see the bubbles at the top and that's clear? So that it's already worked, and now you can start to see on the camera here, on the top there, you're getting a thin layer of bubbles. And we'll let that go. You can actually see the individual particles spinning around there. So we'll let that go for a minute. But if we just let it go, gravity's working. And again, it's not working in the same way as magnetics. It's a different force, so it scales differently with volume. And so it solves our problem of trying to find something that you could use at any volume. That actually solves our problem for being simple, too, because everything happens in the container. So there, you're starting to see it clear up. So now, all of a sudden, you can use these tiny bubbles. And I'll just say before I show a picture of these bubbles in the microscope picture, that it turns out bubbles are used in other industries. So these are glass-shelled bubbles. There's also plastic-shelled bubbles. The inside is gas. The outside is a solid material. They're used in other industries. They're used in deep-sea drilling. They're used in composite materials. So if you drove here, there's probably bubbles in your dashboard to lower the density for like composite materials. So we saw that and we said, well, maybe we can use those. Maybe we could repurpose them. We can come up with protocols. We can come up with ideas and systems to actually take advantage of that. And so there, it's about done. We can come back to it if we need, or just leave. Is it possible to leave the one up on the side? Okay, let's do that. So here's what they look like. So there's a bubble, and there's a cell. So same idea as the particles, but now all of a sudden, because it's a different force, you can do different things. So that's this is just a schematic of that. So again, everything that's happening there, so your cells you want to keep, say, or to separate out, they float to the top. So it's like in that video. Everything else sinks. So it gives a very nice sort of separation axis. And then what you can do is it brings those bubbles to a place where you can easily remove them. And so we've engineered ways to pull the bubbles off. We've engineered ways to mix. We've engineered all these ways to make this process very, very simple and very easy and scalable. So we made a better way. So that's exciting. That's, again, what we've done at Acadium. And that's a company we started. I'll talk a little bit about, just a minute at the end, about some of the things we've done I think Tim did a good job introducing the technology. But it's for these reasons that the technology has received awards, that the team has gotten recognition for this kind of thing. And it's been a really exciting journey to be solving this problem. Okay, but being a scientist, that's cool. But we never stop, right? That's just the way it is. How can we make it better? So an interesting thing happens here. So this is I think this might be my last demo. I think it's the last demo. Let's see if we can, I got to pull this off here. This one's just clicked. So if you notice, that took a few minutes. So it's clear now. So it's done. So maybe that was like 4 minutes. But what if we want that to happen in like 2 minutes or 1 minute? Man, that's a lot of string. So what can we do? So one idea we had was, what happens if we bring stuff together, so in a clump, right? So instead of one bubble, you have like 10 bubbles. So I'm going to release these at the same speed. So there's 3 scenarios. This could go faster, this could go faster, they could go the same rate. So who thinks they'll go the same rate? Okay, about a third. What about this one? Who wants to vote for the little guy, the underdog? Okay, of course, Jacob wants to vote for the underdog. What about the big clump? Okay, so you're all the ones that should stay in science. I'm just kidding. All right, so we're going to go at the same time here. So let's see what happens. See which one goes first. Who's winning? The big one, okay. So when you bring them together, you get this clump effect where they rise faster as a unit. And so again, thinking about engineering, you can start playing with the shape of the container to encourage that. Like you could turn it on its side first and then stand it up, and then all the particles go to one side and then go up quickly together. But if you plot it out, it looks something like there on the right, where the more bubbles that are together, the faster it rises. So if you take all the bubbles like in that demo over there and just pack them together, it's a clump that'll just go really quickly. So what's cool about this is, I didn't spend time talking about this, but magnetics actually, the only reason magnetic particles come out of fluid is because they form chains. And then once they form a chain, they come out of the fluid. That's actually how you get, like you saw how fast in the small vial they came out. That's why it works. So we basically thought of the analog to that for microbubbles. And then we went and patented it. So that's if you're interested in looking that up, the patent reference is there at the bottom. And then you could do more things. Something happened to my next image here. I'm not sure maybe it was when we flipped the video, I don't know. But you can also combine this with methods. So what if we combined magnetism with microbubbles? Like what if I could take a cell and put a magnetic particle and a microbubble on it? All of a sudden I could pull with both gravity and magnetism. So there's all kinds of reasons you'd want to do that. You can actually make a separation process that gives you higher purity. So purity is one of the big figures of merit in the industry. And so that's something we've also shown as well. And again, if you're interested, well, the patent there application is, actually that's an issued patent now, but if you're interested, I can show you after. But this is what we work on. So when people ask me what I do for work, I used to say I play with magnets. Now I say I play with bubbles. So see, everyone should be a scientist, right? Okay, so that's it for the technology, really. And I just wanted to kind of share some demos and share some different things. Just a minute about the company. So we're located here in town. Does anyone know where my HQ is? Have you guys heard of this, my HQ? It's Wagner and Liberty. So it used to be the Paul buildings. They've repurposed those. There's a lot of tech companies in there now. So that's where we're at. It's a great place. So there's 7 of us full-time. There's many more that help us. But in this sort of core team, and it's been very exciting, actually, to work on this team. I mean, it's very talented people. And it's fun because we get to accomplish and do things like this. And there's a lot that goes into it. A lot of times before you start these journeys, you never know how challenging or how much time it's going to be. But we've been able to accomplish incredibly high purities, which is, again, the figure of merit. We've done that with bubbles, this new material that nobody had ever used for this before. We received Best New Technology, like Tim said. And right now, people are using this. People are testing it. We work very close with users. That's our philosophy, is as soon as you have something ready, try to get it out to somebody to beta test it or to try it out. And yeah, we've done the whole venture capital thing. It's been interesting as well because we've worked with both local investors and investors from Silicon Valley. And there's a few of them up here, so a lot of this has kind of spanned the years, but more recently with Acadium, so instead of putting granting agencies up for Acadium, we put venture capitalists up. But it's still with the goal of trying to do something useful, trying to improve the world, and then putting together the team and the resources to do that. So with anything like this, there's always many thanks, and it is really, for me, it's not just about the technology. My belief now is it's more about the people than the technology, because if you find the right team, you can really do anything. And so I've been fortunate enough to work with a lot of people. There's a few people here today. Nadia from the Acadian team is here. Jean from the Intubean team is here, who worked with on prototyping. And of course, many of you here too, also family and even former physics professors and things. And it's just interesting to see what goes in to trying to make something work. And again, my whole goal is to try to invent things, develop things. And so I think about that a lot, like what are the ingredients to make these discoveries, to make these applications. And thank you, actually, for spending your Saturday morning with me. And hopefully I accomplished my goal of not giving you a reason to go drink or drink more on St. Patrick's Day. So with that, I'll hang out for questions, and thank you so much for having me.